Thank you for coming on Friday on the half-term week when all people are on vacation and the tsunami of football that overwhelm the city. I don't think I need to introduce Satya. I spent the last 20 years here building computational physics. I will say that it's a great pleasure to have him back. Those of you who aren't in LIGO haven't heard much of Satya for like the last 5 or 6 months. Those of us in LIGO have heard quite a bit from him. He's been the co-lead of the team writing the paper for the latest gravitational wave detection. So it's a great pleasure to have him here for even a brief visit to tell us about this new discovery. And I will say after the brief talk, we're going to have a celebration in the rest frame with some bubbly and some nibbles. And we'll have a brief chance to chat with Satya before he has to take off again for Heathrow. Satya will be back in 2 weeks for a couple of weeks. So we'll have another chance to speak with him now.
Excellent. Thank you very much, Patrick. This was meant to be my 1 month visit to Cardiff, but in between I'll be going and coming back. So today, thanks for the opportunity. This is the first talk on the new discovery, GW170104, which means it was discovered 5 months ago, 6 months ago, depending on how we count the number of months. In the Hindu calendar, probably it's 6 months. So we made it to the cover again. It's another binary black hole collisions at a redshift of 2.2, which is our largest thing. So what did we observe? So before that, I want to really thank the 3 collaborations that made this possible: GO600, LIGO Scientific Collaboration, and Virgo. There are people from 15 different countries and 80 different institutions. Hundreds of graduate students and postdocs. They are the ones who really do the bulk of the work. It's an engineering marvel as much as it is a scientific discovery that we make. And so many thanks to hundreds and hundreds of colleagues for helping this out. So what did we discover? This is another observation of a binary black hole merger. The second event, if you remember, which was discovered on the Boxing Day, was not visible in the data stream directly. So we had to do quite a bit of explaining. But here is another event, which is in the same category. Even though it's only half the signal-to-noise ratio of the first discovery, the signal is pretty much visible. So what do we have here at the top? It is the strain amplitude in the 2 detectors. In red, you see from Hanford, and in blue, you see from Livingston. We have to invert the sign of one of the detectors relative to the other because the 2 detectors are oriented by an angle of pi degrees, and we have to shift the data by about 3 milliseconds in this case, and the 2 strains then agree beautifully in that part of the signal. So 3 millisecond delay arriving in Hanford first and then Livingston. And if we then subtract the best fit gravitational waveform that we plot here in black from the data, then what is left over is consistent with detector noise. We don't detect anything excess, and it's completely consistent with data at other times. The signal to noise ratio is about 13. The significance of this event is that purely noise would produce such an event only once in less than 70,000 years. If we use what is called model independent analysis, that would raise to something like 1 per 20,000 years, but still this is an extremely significant event. Now, Cardiff contributed to the development of the models that are used in order to learn about what the system is, or generally any binary black hole system is. And in black here, you see the detector data again, but unlike in the previous case, where it was band passed and lines in the spectrum removed, nothing of that sort. We don't need to do that in our real analysis. You simply take that data, whiten it, and then you filter it with the model waveforms. The red one here represents unmodeled search, where you don't make any big assumptions about what is there in the data. You just use a bunch of wavelets at each point and you fit it and you reconstruct the whole thing, and that is what that red trace is. It cannot do very well unless the signal to noise ratio is high or the signal is short enough that all the energy is focused in a few cycles. And we see that reconstruction on top of that is in blue, the binary black hole waveform models developed at Cardiff, which are used to characterize what the signal is, and it very tightly agrees with that wavelet reconstruction within error bars. The wavelet reconstruction does not do very well at lower frequencies where the signal does not have any great strength, and that is depicted by it being very broad. The error bars are very large, especially in the Livingston detector. You can see that more clearly, whereas in the Hanford detector too, that's very clear. So the model independent reconstruction and the model dependent, that means the template waveforms of Cardiff, agree beautifully. I want to spend just another 30 seconds telling you the importance of this Cardiff contribution, because without it, we are nowhere. It's true that the full solution, the exact solution to the two-body dynamics, requires full numerical relativity simulations. They are also done at Cardiff. But just those numerical relativity simulations are not enough. They are done in many other groups around the world. The biggest contribution that Cardiff made was to convert them into analytical waveform models, which are fast. Instead of taking 1 month to generate one waveform in the parameter space, it takes only tens of milliseconds. And that is the big contribution this group has made, and it really makes me extremely proud, because we couldn't have said anything about the model characteristics without those. The other competing analytical models elsewhere in the world, but they are very slow, hundreds of seconds instead of milliseconds or hundreds of milliseconds. So 1,000 times faster. Maybe exaggerating that a little bit, but not a lot. I mean, it's maybe a factor of 2 to 5, not a lot more. So that was what was measured. And it beautifully agrees with general relativity that I will tell you in ways that does not violate any predictions of GR. Now, the masses of the component black holes are the ones that come out of this analysis using these waveform models. And you can see it happily sits filling the gap between our previous detections. There are two firm detections, 150914, the first discovery, and the Boxing Day event, which sit here. And this happens to be in between, but slightly on the heavier side. So the component masses at the center of this is about 19 solar masses and 31 solar masses, totally 20 solar masses. And we are now seeing a pattern. So one of the statements that I made during the press conference was, once is chance, twice is coincidence, thrice, well, Ian Fleming said enemy, but thrice is pattern. I mean, you can see there is a pattern here of heavier black holes that were not seen before LIGO discovered them. So we're detecting a population of new black holes, and we are opening black hole gravitational astronomy, or black hole astronomy, if you wish. Now, the spins of these black holes cannot be measured very well, but what we can show you here is in the plane of the spin. These are called spin disk plots, and the left-hand one is for one of the companions, the more massive companion, and the second one is for the lighter companion, and this is for the Boxing Day event. What is shown is the probability density for the magnitude of the spin, which is the length of the vector from the center to the edge of the disk, and the depth of this color tells you how much of probability density is there and how the spin is oriented. I mean, if this is along this line here, that means the spin is oriented along the orbit. If it is perpendicular, of course, the spin is perpendicular, and it is anti-aligned if it is in that direction. So here we see for the Boxing Day event that there is very little chance that it is zero, the spin is zero for these heavier black holes. For the other black hole, we cannot really say anything much. So this is the first time we had conclusive evidence that black hole spins could be of order something like 0.2 in this particular case. Here, this is the event, 170104. For this secondary, we cannot tell anything. It's all over the place, the posterior distribution. But for the primary, it looks like there is a little bit of component anti-aligned with respect to the orbit. In this case, aligned with the orbit, this anti-aligned, but note that it is really consistent with zero as well. The distribution is still not as tight as in this case, but there seems to be some slight evidence that it is anti-aligned. And that's an important one for reasons that I will mention. Looking at the same result in two different ways, the component of the spin perpendicular to the orbital angular momentum is called chi p. The effective spin, which is a combination of spins that is projected along the orbital angular momentum, is shown here. In gray, here you see the histograms of the prior in green and of the posterior in blue. And what you see is that there is not much difference for the perpendicular component. It's also called the precessing component because it is the one that is responsible for precession of the orbit. Whereas the effective spin is tighter than the prior, and therefore, I mean, this has a slight preference, as I said, something like minus 0.12, but it is still consistent with zero. So what are the astrophysical implications? We will come to that in a minute. This is some of the measured parameters. We measure many more, or infer, in some cases, parameters. The primary black hole mass, 31, and secondary 19, as I said before. The total mass is about 51 solar mass, and the final black hole mass is about 49. So it lost roughly 2 solar masses as compared to 3 for the first discovery. The peak luminosity in all these cases, if the masses are roughly equal, is all same. And as we say, for that little time, the luminosity exceeds all the stars in the universe, in all the galaxies. So it's a phenomenal luminosity, the most powerful events in the universe, really. The effective spin parameter, I mentioned that. Sorry?
What is the chirp mass?
Oh, the chirp mass is a combination of these two masses, which is... So you have M1 and M2, which are the component masses, and from them you compute what is called the symmetric mass ratio, which is this quantity, and chirp mass is this nu to the 3/5 times m. Why is that so important? Because that is the combination, purely because of Kepler's law, that is the combination of that comes in determining the orbital dynamics of a under radiation back reaction. And that's the reason why it's sometimes important for some people in the community, and so we quote that. The distance is 880 megaparsec, roughly 2 times farther away than the previous ones. The final black hole spin is boring 0.64, as in the other cases, and redshift, as I said before, is 0.2. Okay, now what are the implications for astrophysics? There are two main formation scenarios by which binary black holes can form. One of them is binaries that form from massive stars, which are already binaries in the field, and then formation of these binaries in dense stellar clusters. Very quickly, you can have 2 main sequence stars that spend millions of years of order 10 to the 4 observed in the galaxy. These are 2 OB main sequence stars that evolve. One of them fills its Roche lobe, mass transfer, and all that. There are lots of things that happen, but the important one is that one of them undergoes a supernova and a kick. And if the system remains after that kick, the other one, the less massive one, fills its Roche lobe, mass transfer, goes on for tens of thousands of years. And then it can form an object like this, in which one of them is either a helium core of the secondary with compact companion inside, and so on. That can go on for a little while. And you can either form, finally, after the explosion, the second explosion, which is here, you can either form 2 compact objects, or you could disrupt the system after the secondary supernova. And of course, if you succeed in forming a bound system, which evolves purely by gravitational radiation reaction, it undergoes then merger within the Hubble time, and that is what is observed in the LIGO band. Of course, if the system gets disrupted, which might happen to most of the systems, we won't observe them. The other scenario is to form individual black holes in dense stellar clusters. They evolve, the massive stars evolve, go through supernova, they form black holes, but then they sink into the center of the cluster where they find black holes that have already sunk in from before and maybe paired up with other black holes, in which case there are different kinds of scatterings that can happen. You can have a binary single scattering. The black hole comes in and disturbs the binary but otherwise goes away. You can have binary exchange that can happen. One of the black holes in this could be replaced by the new black holes that comes in. You can have binary scattering, binary single exchange, binary exchange. All these things can happen over millions and millions of years. You can see how in a particular scenario that was created to explain the first discovery by this dynamical formation mechanism. What happens eventually is that a scattering can result in these black hole pair to be ejected from the dense stellar cluster, after which it happily evolves without being interrupted by a third party, and so finally merges, and we observe it in the LIGO band. These are the different scenarios. In the first scenario, they co-evolve. The spins are more or less aligned because of the co-evolution, the way the Roche lobe fills and drives the systems. They're more or less aligned spins. But the supernova can disturb those alignments. There's no problem. But if the supernova is too large and makes the system very misaligned, then the rate of binary mergers will decrease, because if the supernovas are large, then you can't merge them. So there is this tension between the rate of mergers and misalignments in the isolated binary formation. In this case, there's no such tension. You can bring the two black holes in later in their lives, and therefore have spin orientations in whatever way you want. And in this case, binary spin misorientations are more easily accommodated. Now, we have measured these spins. One of the spins seems to be misaligned. We can't tell whether it is really anti-aligned, misaligned in the sense that it is tilted and the projection is negative. We can't tell at the moment. More louder signals can actually give us that information. Again, from using Cardiff-based models, we can measure those spin precisions and so on, but at the moment we can't do. So there is a slight preference for this dense stellar cluster model, but it's not a done deal. It's not completely conclusive. The other astrophysical implications, that's basically effective spin that we measure. I talked about that. That's what we measure. The rate used to be 9 to 240 per year per gigaparsec cube from the first observing run. Now we have slightly constrained it. The upper limit is not so very well constrained. It remains, as a fraction, it's similar. But the lower limit has significantly changed from 9 to 12, which means that models that predict either low rates because of large kicks or high metallicity or whatever, and models that don't predict heavy black holes are getting constrained because of these. I mean, especially those that cannot predict heavy black holes are getting severely constrained by this. So the rates are roughly consistent with whatever was previously estimated, and our detection is entirely consistent with being a population, astrophysical population. In reality, of course, it will not be possible to rule out any of the models. Each one of those has something like a dozen different subdivisions. There are 22 models for the isolated binary evolution, and there are half a dozen models for the cluster dynamics. We can't really rule out unless we have large populations, because they predict, each of those models predict different mass distributions, spin distributions, mass ratios, and so on. So once we have those, we will be able to tell. So that's the astrophysical implication. We also carried out tests of generativity. As I keep emphasizing in every lecture, in the solar system, the dimensionless gravitational potential is something like 10 to the minus 8 or 10 to the minus 6, even for the tightest orbits. Whereas in radio binary pulsars, this can be as large as 10 to the minus 4. What I'm talking about here is the dimensionless potential phi, the potential divided by c squared. Okay, this is a dimensionless quantity. And that is the quantity that is of order, really, something like 10 to the minus 6 to 10 to the minus 7, maybe in the solar system. Whereas if order 10 to the minus 4 for radio binary pulsars. So, but in the case of binary black holes, that number can get to 0.5. And that's the reason why they are the best tests of generativity. Test beds for generativity. What we tested in this particular case, in addition to the previous ones, is the propagation effects. Because the system is at a redshift of 0.2, we thought it is best to look at if there are any deviations from generativity as far as the propagation of gravitational waves are. So the dispersion relation in generativity is E square equals P square C square. So gravitational waves travel at the speed of light. But there are a number of theories of gravity in which the dispersion relation is modified by this additional term, an amplitude A times Pc to the power of alpha and index alpha. So what we can do is to work out whether or not this effect is present, namely the different frequencies travel at different speeds, and look at what constraints we can place if we don't discover any dispersion of gravitational waves. And so we didn't really find any evidence for the dispersion of gravitational waves. I'll show you in a figure what that means. But these are the first constraints ever in the gravity sector for superluminal gravitational waves. There have been constraints on subluminal propagation of gravitational waves by Bremsstrahlung and other results, but this is the first time we are setting limits on the superluminal propagation. Now, Bremsstrahlung is also, superluminal, it's just that it's not as conclusive as what we have. Right, so I introduced those parameters A and alpha. They can take any value in some theories of gravity. In certain theories of gravity, they take specific values, in typically integer or half integer, which is the reason why we chose these half integer values, but they can be any value. And what you have here is a constraint. Different A's have different units, and so it is pico electron volts to the power of 2 minus alpha is the upper limit that we are setting. And if you have these boxes filled and downwards, that means it is subluminal. If it is filled up, that means it is superluminal. And these are the limits. There is a trend here, and we understand what that is. And the pico electron volt really comes from the fact that the graviton energy corresponding to the peak gravitational frequency, which is about 250 hertz, is precisely pico electron volts. So we are exploring graviton energies. We can't really detect individual gravitons because our detectors are flooded with gazillions of gravitons. So there's no question of detecting single gravitons. But if you think of the energy equivalent of these energy equivalent for gravitons by the hypothetical particles of gravitational waves, then that corresponds to pico electron volts, and that's the reason why that scale is a very nice scale in which to plot. And if purely in terms of electron volts, then this is at the level of 10 to the minus 44. So the constraints that we are placing is really extremely impressive for these things. In summary, then, this figure says it all. This is the first discovery, the heaviest black hole pair that we have so far. This is the second one, the lightest that we have, and this nicely fills the gap left by those two. With those comments, let me thank you very much, and my apologies again for coming late. Thank you.
So I know you have to take up pretty quickly.
No, it's fine. I mean, 11. Yeah, I'll be here until 11.
Questions for Satya? Yes?
There seem to be the components that merge seem to be of comparable mass in all four cases. Is that a selection effect?
Yeah.
Is it telling us something?
Yeah, absolutely. It's also true for the heavier systems. We can see the sweet spot of LIGO detectors is really for this object. If you look at the sensitivity curves, then this is where we have the best sensitivity. So we are already biased just that no one believed that such black holes existed except Leonid Grishchuk, who used to say the first things that we are going to see will be binary black holes. He made me write a paper with him about this in 2001, the first events of LIGO. I mean, that was the title of the paper. So indeed, that's what we are seeing, but it's just that astrophysically we never expected to see. And the whole sensitivity of the instrument goes like this nu to the 3/5. And if the mass ratio is small, then we have less likely to, the volume of space from which we observe is less. So we are really biased towards observing equal mass, heavy systems up to about 100 solar masses.
Can you go back to what you had at the beginning with the waveforms of the model?
Yeah. I don't know which one, maybe the next one, yeah.
No,
One before, yeah.
yeah. So the residuals on the bottom, just after where the peak is, it
Yeah.
looks like they line up really well. The residuals for a couple of bumps. Is that suggesting that the model is missing something there?
Thank you very much for that question. We discussed this for 2 weeks within the collaboration. And what was necessary to do is to do this by injections over and over again. This is the reason why it takes a long time, and to see whether that is significant. Just on the third day after the subtraction, we recognize that there is something here. No, there is nothing. Absolutely nothing. It's completely consistent. You can say sometimes it just kind of gets aligned and then misaligned. But really, you really did a fantastic thing, because we spent a lot of time discussing this. Thanks for that question.
The idea of a supernova leaving such a big remnant behind, is that?
I think it's a low metallicity. It's telling us that the metallicity is low. I didn't put up some of the plots. I wanted this to be more a dialogue rather than just me talking all the time. So you're right. The only way this can happen is if the metallicity is something like 0.5 solar, or maybe even less, 0.3 solar. Of course, the smaller you make the metallicity, the bigger you can make these black holes. But you can't make them 10 to the 4 solar masses, which is what our friends in large-scale structure want. Maybe 10 to the 3, 10 to the 2, 10 to the 3 is fine, but after that it's very difficult.
Can LIGO detect events that are not black hole mergers? Can it detect other things?
Yeah, we look for 1 solar mass compact objects all the way to 500, total mass of 500 solar mass objects. We look for all of them. These are the ones that we are finding. Before the first discovery, we used to think that our first detection will be binary neutron stars. The expected rate is such that at the nominal rate, we expect 1 event per year in the current sensitivity. We have taken about 6 months of data, 50% or even less, 30% duty cycle. So it's not a lot of data. We don't really expect much, but it could happen. We might discover. We haven't done we haven't completed all the analysis yet. And the data is still being taken. It will be taken until the end of August. The real time, we expect to make frequent detections of these binary neutron stars in about 2020, when we expect these detectors to reach design sensitivity. Yeah.
Any comment on the superoptimal counterpart?
That's a wonderful question too. This particular trigger was circulated to our EM partners within a couple of hours. I believe about 30 groups have followed up, and we will have reports of those. There was one group that had reported a gamma ray burst counterpart. I don't know if that stayed. I think it went away. But there are other groups that are reporting some afterglows within the region, but it's not our result. You will see these very soon. I think they posted it to the archive last night. It should, right? Have they appeared already? Yeah, yeah. They are there, out there. Some of them are curious, I would say. Yeah.
Can you say something about the future of LIGO developments and what we're likely to see over the next few years?
Yeah. So at the moment, we are still about a factor of 3 in strain sensitivity away from where we want to be. That means a volume of space that is 30 times larger for binary neutron stars, typically factor of another 2 more for binary black holes. So we'll be discovering these binary black holes more and more. At the moment, it looks as though this is another system, but binary black holes have an extremely rich dynamics. The dynamics that is, unheard of in Newtonian mechanics. Precessing of the orbital planes is one that I mentioned, but higher order modes and black hole spectrum. The final remnant that settles down has actually infinite spectrum of modes, and we have not yet seen even the first quasi-normal mode decisively. We see a ring down signal, but we can't tell whether it's from a black hole or something else. There are hundreds of other things that we can do when we get these binary black holes with large signal to noise ratios, lasting for longer and whatnot. Those are the kind of things that I expect for the binary black hole variety. But in addition to that, maybe an occasional supernova would be good. But our detectors are sensitive only to supernova within the galaxy, and therefore the chance of seeing them is maybe once in 30 years or once in 100 years. But so we need really second generation detectors to observe supernova, which will be able to track them up to about 5 megaparsec to 10 megaparsec. One thing that will happen, maybe in the advanced LIGO era, is a stochastic background of gravitational waves from binary black holes. Because once you start to sample a larger part of the universe, you will start to discover the confusion background coming from binary black holes. Binary neutron stars, definitely, but maybe small black holes falling into big black holes. That has another great variety in the waveform models. Neutron stars falling into black holes is not known in astronomy, but we believe they must exist. So that's another object that we expect to discover. For me, it's not really the next 5 years that is important, maybe the next 50 years. Because just as CMB was targeted for nearly 3 to 4 decades and finally detected these cosmic, the fluctuations in the cosmic background. The real physics from the early universe, the only hope of learning about it is the stochastic background. And we have to find a way of detecting them. It may take another 30 years, 20 years, 30 years. But that is where we need to be getting. Thank you.
Great. Well, thanks, Satya, again.